Thanks a lot. Welcome. Yes, so this talk is about wide field of view displays for AR. To give you a little bit of background on both the display that we used and some of the methods that we used, here's some, let's say brief introduction. On the left side, you see the display that we use. This is the display developed by Kiyoshi Kiyokawa. It's basically a very wide field of view display that makes use of two projectors and a hyperbolical mirror, which basically projects on top of the screen, which consists of retroreflective material through which you basically can see the content. And this theoretically has a field of view of 110 by 66 degrees of view, which we did not fully use, but most of it we did, which we'll see later on. In the middle, you see a picture of the human visual field. Just as a reference, I will come back about this again a little bit later. As you may see here, and you might have seen this image before, vision basically performs quite differently in central vision as in the periphery. So in the central vision, you can read text, which you cannot do in the periphery. There's a good brightness and contrast perception in the periphery, but not a lot of color, for example, that you can perceive there. And this might have an influence on how you present and also notice information that you present in those areas. However, there's not a lot of material in AR that actually looked especially on those topics. On the right, you see quite small, but still hopefully recognizable, the two methods that we used in at least the first study that I will present, namely in situ and in view, view management, meaning that in situ basically shows you a label on top of an object and it's only visible when you have the object in view, whereas in view management basically shows you a leader line to the object that it is referring to. This research builds on top of a previous study that we presented a couple of years ago at ISMAR that basically was performed using the display in a divided attention task. Users performed the divided attention task, meaning that they played Sudoku on a computer. And once in a while, every 10 seconds approximately, a number of objects would appear around the user, of which one of them was actually a target or could be a target. So we timed it, of course, in such a way that people could not recognize basically that every time the objects would appear that there would be a target, but sometimes there was a target. We compared there the in-view and in-situ view management methods and basically looked on the effect of field of view. So we simulated different field of views in the display that I just showed you before, from rather small to a little bit larger. I'll show you the exact size of those field of view in a moment, just as a reference. And what we found out there is that basically performance of in situ improves, while in view performance decreases the bigger the field of view, basically. It's quite logical because you can see basically a linking line to the object that's referring to, so it's quite easy to notice where a target is when the field of view is small, whereas this is not so hard. It's quite hard with in situ. Basically, we noticed that there would be a kind of equality point at 130 degrees, which is an important notice because I will reflect to this later on. Well, more areas in the peripheral targets and basically very little effect of field of view on response time and a mental workload. To follow up, basically, I'll present you two studies here. The first one is basically directly continuing the thought that we had in the first paper by looking now into a, let's say, mobile search task where people really move around instead of looking very concentrated on a small screen, which is quite different. And a second study which looks at, let's say, fundamental label characteristics on noticeability. So how can I design labels that they are well noticeable for people, and how do they react basically in the different areas in the peripheral vision? Why do we do that? Quite simple, to improve view management, especially for wide field of view displays, because there's not a lot of work around it. Tobias Hiller is one of the people sitting here who did a study some time ago in their large display, basically simulating different fields of view, but there's not a lot else. Also, it's quite sketchy actually what happens with information in peripheral visual fields. There's a lot of work in perception, but it's not always clear how this affects AR. So, first study basically is using the same setup. So we're using the same display as described before. And basically, people were walking around. We had a path of approximately 800 meters around the campus where they had to go back and forth. They did this 8 times, basically, for all the trials that they had to go through. And once in a while, illustrated by the red dots, the objects would appear again, and one of those objects could be a target. And this target would be basically recognized by the label that would be referring to it, meaning that we again had in situ and in view labeling to basically compare both the methods, again in the same field of views that we have done before. As I said, on the next slide, I will show you the exact field of views, but this is important to note. So we had the same field of views, we just had a different task right now. Targets in this case were approximately 20 meters away, above the ground, looking somewhat in the size of a billboard. The actual labels were shown approximately a meter away from the user. As said, we used in situ and in view. The different measures that we took were discovery rate, response time, walking time, subjective feedback, including also nasal-TLX. So just as a reference here, the different fields of view. As I said, this is the same as the old paper. Where you can see that actually the yellow box is the biggest field of view, and the smaller ones are the smallest ones, of course. The small ones only basically cover the near periphery, the larger ones also the far periphery. But of course, what you can see here already is that basically a large part of the periphery is not covered. So this is still basically a work to do for future displays. So what did we find? Well, first of all, quite similar to the old study is that in view and in situ labeling worked similarly, meaning that in view labeling worked worse with the wider field of view, whereas in situ would improve their performance. However, as I told you before, we had a point of equality at approximately 130 degrees before, which we calculated. We could not, of course, detect it because the field of view was not covered by the display, but we calculated it, and this was slightly better here. So we had a point of equality approximately at 100 degrees field of view, which is somewhat better. Response times were relatively constant, so there was not a lot of difference between both. However, we had higher discovery rates with in view, meaning also that overall time, including the whole walking period, was longer with in view because basically people noticed more. How it actually occurred was that most of the times people would walk around when they basically were shown the targets, they would actually stop. So only very few people actually walked through while looking around, which was also quite difficult because the labels were basically completely around the user with 20-degree intervals. Again, field of view did not significantly impact their perceived workload, similar to the first study. And higher field of view lowered the ease of noticing, especially with in-view labeling. As I said, the wider field of view, the less effective basically in-view is. Ease of focusing on walking was lower with in-view labeling, but it was not impacted by field of view, which can be probably explained by the fact that everybody can walk around basically quite easily without really concentrating on it. Okay, so that was the first study. Second study basically took on, from this point of view, where we thought, okay, actually, how can we design labels as such that if we actually indicate that there's something on the right or far left side, how to design this actually. So what kind of methods can we apply, what kind of colors, etc., what kind of different label characteristics can we study to basically find out what's the best and under different conditions. What we did here was to compare the optics see-through display, again, the same one that we used before, with the video see-through, just to have a slightly different conditions also within a controlled environment this time. So we had video backgrounds, which I'll show you on the next slide, which will basically cycle through and watched, and those video backgrounds were very different. Is that I will talk a bit more about this in a bit. And basically we would show the labels over the controlled environment, the video background, to basically see if there was an interaction between this video background and the actual label parameter that we were changing. We did some luminance measurements here to basically make the colors equally bright, because of course this should be the case, otherwise we're basically pulling some colors forward, so to speak. What also should be said here is that based on the luminance measurement device, the video background was slightly brighter in the OST, where the labels were less bright, whereas the VST had a lower brightness of the actual video background, but a slightly higher brightness of the labels themselves. So there's some slight variations here. So what did we change here? Well, basically we had the video backgrounds. I hope the top one is also playing. Let's see if I can get this going. Yeah, oops, okay. So lower background, rather hectic background, a lot of people moving through there, lots of bright colors, flashing colors, whereas the top one basically has a more equal shape and less movement basically. And we wanted to basically see how the label characteristics basically reacted to the different backgrounds. So we had a grid where we showed the labels on, and we basically changed color, motion, and size of the labels. And we showed them in the different locations in this grid basically and analyzed later on if there wasn't any effect. So we had 7 different colors, which you can see there. We had different kinds of text sizes, so the label sizes, and we had different movements. We show here 3 on the right, horizontal, vertical, and circular. We also had blinking and basically no motion. What we did afterwards was to analyze the measures and analyze them on location, on region, and also on background. What we did was to make basically a pixelated view of the background, to see if there's an interaction. I'll show you the image in a bit. And also a background analysis on optical flow. Basically, what we found out was that blue basically over-trumped basically everything. So in OST and VST, blue was preferred everywhere. We had a bit of a brighter brightness contrast with the blue color, which somehow was affected by the background. Sometimes red was more likely than blue, but basically blue was the best, even though yellow had the higher contrast. For movement, we basically had blinking scoring best in the OST and circular for VST, which somehow could be explained based on the background because the movements in the background were quite different from circular and blinking motions. However, they were also preferred in those areas where we had no motion at all. So we don't have really an explanation for that. Finally, quite as expected, larger size labels are basically better for further down the periphery. Briefly, a couple of points on discussions. As said, the results were largely coherent. In the first study with the old study that we showed on search performance, there's some issues that we need to take a look closer at. Pre-attentive processing of information in the periphery, which we could not do right now. Basically, color, size, and orientation are pre-processed. We don't know exactly right now how this affects the performance. And we actually had some contrasting findings based on reaction time, response time, sorry, where at least for very small fields of view, we did another study which we presented this morning, we could actually find an effect which we could not do here. There was no effect on mental load, which is kind of strange, but we don't know yet what it is about. The whole interaction with the background is still an open factor. So actually we did quite a bit of analysis, but there can be done more, basically also in the field of vision and asymmetries, where we basically want to look at the difference basically of the stimulus that we have in the label and the background stimulus, where there's quite a lot of research on in perception research, however, always when looking at the label itself and not by noticing it in the sites. Blue, I have to speed up because I'm already 30 seconds over. Blue coincided also with the highest brightness contrast and subjective preference. So there might be something here, but we don't know yet about that either. And the motion difference is unclear to us why this happened. If this is a cultural preference or something else, we don't know yet. So to conclude, we showed different results on labeling aspects for search performance and noticeability. Next steps are basically to also combine these methods and comparing in different kinds of displays. Also looking at eye tracking, because we always said, okay, people have to look straight ahead when noticing the colors in the periphery, so that they were not allowed to look at it. This is an important point, which I forgot to tell you. Of course, we were not always sure if they really didn't look, but we had basically a marker. And finally, we would like to see how this works in real life conditions. So with that, I'm slightly over time, but thank you anyway. So.
Fine. Thanks, Ernst. Do we have any questions? So maybe I'll have one.
Okay, go ahead.
So in the background studies, you were measuring design of experiment considering divided attention task. It seems that you didn't apply the same design. Yeah, why? Can you explain why?
Basically, we actually considered that, but it would have been a different task. So we first wanted to do in singular attention, basically just focusing on the background and then basically seeing how things would react in the site. We considered doing a divided attention task, but thought it would introduce too many new factors that would make analysis quite complicated. So we avoided doing that in the second experiment for now. But it would be an interesting one for the future, basically. So, okay.